Welcome back. Hope you're doing well. We have been discussing limits of functions for now. Limits of functions because there's a lot of different ways to be able to approach different points at a function and be able to discuss the different ways that things can either fail to approach or approach in a specific way, infinity or negative infinity, in all of these different kinds of scenarios and contexts. Now, we want to talk about something called continuity today, which is essentially going to be taking that definition of limit and cutting off a little part of it. Remember that we have said that as a function, f sub x approaches L as x approaches x naught, whenever you have the following. Whenever for all epsilon, there exists a delta, these, of course, being values that are positive values, such that whenever x is minus x naught an absolute value is in between 0 and delta, and indeed it needs to not include 0, so it needs to be strictly less than, and that's going to imply that f of x minus L is indeed going to be less than epsilon. Now, in order to do continuity, we only need to change really two things about this definition. This tells us that f of x approaches L, but when we ask for something to be continuous at a point, we ask for it to converge to the point itself, the point that you would hope that it would have converged to. One thing first, though, is that we have to ask for the function itself to be defined at the point x naught. So what that means is that because we are asking for the function f to be defined at x naught in order to make something continuous, well, the way that we get to change that in our definition is that we get to remove this little 0 is less than this absolute value. Notice that this is gone now, right? So we don't need that anymore. The second is that we ask for the limit to exist. So f has a limit at x naught. That means that there exists some value L for this to exist. And then the last thing is that we ask for that limit to equal something in particular. We ask for the limit of f of x to be equal to f of x naught. So we were replacing any time that we see L, we are replacing that with f of x naught, the value that we're looking for. So this becomes f of x naught right here. Now, this is the definition of continuity. Notice that us taking out the 0 is less than this absolute value of x minus x naught, right? That little 0 is less than part is okay now, because if you actually have x and x naught be equal, then these two things are now equal to each other. So this doesn't break the definition to take out the 0 is less than. We are asking for the function to be defined at this point, and we wanted this limit to be f of x naught. Now, this is going to be the common way in which we use this definition. And indeed, that's the definition that's given right here. Because any function that is continuous at a point here is going to ask to satisfy these things. Now, notably, something that is missing from this definition here are the words accumulation point. There's no notion of an accumulation point here at all when it comes to this definition. In particular, you can have an isolated point out there in the middle of everything. And if you do, then any function on that isolated point is actually going to be continuous at that point because it's automatically going to satisfy this definition. That is, if it is isolated, there is some delta such that whenever you're trying to find all of the points x, such that the absolute value of x minus c here, not x naught, that's c is taking the place of x naught here. When you're trying to look at all of the points x such that the absolute value of x minus c is less than delta, well, remember that that means that there exists an epsilon neighborhood where that's the only point inside of the set, inside of your domain of your set. So you could look at this and say that the only points that satisfy this are the points c itself. Well, c, remember, we said automatically satisfies this last part. So a function that is only defined at a single point is automatically continuous by this definition. But whenever c is an accumulation point of E, then we have this definition that we're used to. We, one, ask for the function to be defined so the left-hand side exists. We ask for the limit to be defined so the right-hand side exists. And finally, we ask for these two things to be equal. So that's the notion here for an accumulation point. Now, we'll say also a function is continuous on an entire set if f is continuous at every single point on that set. And we'll also say just the function is continuous if it's continuous on its entire domain. Note, we do not need the function to be defined on all of R in order for us to say that it is continuous. We're just saying that it's continuous however it's defined. For example, the square root of x is a continuous function, even though it's not defined on the negative numbers for x. So here you can see that if C is an isolated point of the domain, the function is vacuously continuous at C. It's kind of continuous, but it doesn't mean much. It automatically satisfies what you need here. And in the case where E is a closed interval, then we can say that a function is continuous at A, because here A is really only defined from one side, from the right, if you take out, instead of looking at the two-sided limit, you look at the one-sided limit from the side that is defined. So f of a here would be the limit as x approaches a from the right for this function. And similarly, we'll say that a function is continuous at the right endpoint if the limit to the left exists and equals the function value at that point. And that's something that we're going to need a good bit whenever we talk about these theorems that are going to be coming up. Intermediate value theorem, mean value theorem. They all use this sort of notion for continuity. Now, here are some examples for all of this. We've got a function that is a constant function. We know that the limit exists for each of these and that it equals the function a itself. Well, that's exactly what the function equals at each of those points. This is f of c. These two things are the same thing. So the function f is continuous. The identity function, remember the slope one line that goes through the origin, also very nice and continuous because the limit as x approaches c of f of x. Well, remember, this is just the limit as x approaches c of x. Well, we can find that limit. That limit is definitely c. As x approaches c, x approaches c. We talked about that last time as a bit of a tautology. Now, the step function at x equals 0, remember, this one didn't have a limit that existed, so it broke the step 2 that we were looking at from before. So because of that, the function cannot be continuous because no limit for it exists. Remember, a function has to have a limit at a point in order for it to even begin to be considered continuous. Now let's see if we can do some examples with this. Let's take the function f defined to be the square root of x, like we were looking at before. Of course, we're only looking at it on its domain for x being greater than or equal to 0. But right now, we're not going to consider the entire set and ask for it to be continuous. Right now, we're just going to ask, is it continuous at x equals 4? And let's see if we can go through and prove this. Now, of course, just like last time, we have a proof right here to be looking at, but we're going to go through and walk through this one together. And you're going to see that the way that we kind of approach this problem is going to be very similar to how we approach limit problems. We start with fixed epsilon greater than 0, and we're going to choose a delta. Now, that delta, I don't quite know what it's going to be yet. I have to do some scratch work to try and figure that out. Now, we want to show it's continuous at 4. What would it have to approach? If x is approaching 4, what does f of x have to approach? Well, it would have to approach f of 4 in order to work for the continuity. So I don't have to go through and say, okay, well, what's the limit? I know that if it's continuous, it better approach the limit f of 4, which is the square root of 4, which is 2. So I need it to be the case, right? I go down to my scratch work here, that the square root of x minus 2 is less than epsilon. And what I get to work with is that the absolute value of x minus 4 is less than delta. Note the lack of 0 is less than on this first clause. So here we've got the thing that is going to be our scratch work. So we're trying to find a way to write x minus 4 here. Right now I have square root of x minus 2, and I want that to be less than epsilon, of course. So the thing that is, I can get from here to here by doing what? By multiplying by the conjugate. Of course, anything I do in the numerator, I have to do in the denominator. So I could rewrite this in the following way, multiplying by the conjugate of square root of x minus 2. In this case, by the way, we're talking not the complex conjugate like we discussed previously in the course. We're more noting the fact that these two are two terms that are separated by a plus sign or a plus or minus sign, and that we are to flip the sign whenever discussing the conjugate. If I multiply these together, though, what I end up getting is something like x minus 4 over the absolute value of square root of x plus 2. This is the thing that I get to control. But I cannot control the square root of x plus 2, or can I? I think I can. I think I can control what this value gets to be, but I have to be a little bit careful about when and how I get to go through and do that. Right now, I know that I want this to be less than epsilon. And I know that I get to control this based on delta. So I need to try and find a way to get rid of this, the absolute value of the square root of x plus 2. So what we could do is this. We could say, just like last time, let delta be less than 1. And ask, where does x get to live then? Remember, x minus 4 is less than delta. So this is going to imply that x is inside the open interval going from 3 to 5. Okay. So we have this as our setup. Now, for this x value, I can go through and say, okay, well, what is the biggest, or what is the smallest, maybe better to say, that this can be, because that becomes the biggest thing that's multiplied times this number. Well, the smallest that this can be, that is the absolute value of x plus 2, is going to be whenever I plug in 3 inside of here. So I can go through and say that this is going to be greater than or equal to, let's see, we've got absolute value of square root of 3 plus 2. And whatever this is, I'm not actually that concerned. I know that that's going to be greater than or equal to 3. So in particular, whatever this value is, x minus 4 divided by the absolute value of square root of x plus 2, this is definitely going to be less than or equal to the absolute value of x minus 4 over 3. So that's what I can conclude from all of that. Again, I needed for delta to be less than 1 here, because otherwise this could be, well, pretty small. At the end of the day, actually, I could have just said what? Let it be less than or equal to 2, right? I could have just, or I said this is less than or equal to this over 2. And I could have been fine doing that as well. But there's going to be plenty of instances where this could have grown to be as small as it wanted to be. And in those cases, we would not have been allowed to do this. So this is a good example just to kind of illustrate. So now this is the thing we want to be less than epsilon. So if this is the thing that we get to control, what do we want this to be? We would choose delta to be equal to 3 times epsilon. So that when we replace 3 epsilon up here, we divide by 3, and what we get is less than epsilon. Then whenever, and then we just write out the rest of the proof. Whenever we have the absolute value of x minus 4 is less than delta, we have the absolute value of square root of x minus 2 is equal to x minus 4 absolute value divided by the absolute value of x plus 2. And then I realized that I put 3 epsilon up here, even though I didn't really mean to. I needed to put a minimum up here, right? A minimum of 1 and 3 epsilon. And then now that I have that this is less than 1, I can actually control this to be within 3. So this is going to be absolute value of x minus 4 over 3. And then now I know that this is less than 3 epsilon over 3, which is equal to epsilon. Okay, so that gives us what we're looking for. If I wanted to be more illustrative to the proof writer, then something that I could do is I could say, where am I using each thing? Delta is less than or equal to 1, for example, is where I am using the fact that this is going to be with this inequality. And then I could go over here and say, okay, here I'm using the fact that delta is less than or equal to 3 epsilon. If I'm doing that, then I am being a little bit more illustrative and helping the reader out a little bit to know what are the steps that are being taken to get us from point A to point B. And we'll see up here that this is a very similar style of proof where the explanations are baked into the proof itself. Okay, so that gets us through seeing how these functions work and how we do proofs with them in terms of continuity. Very similar to limits, but you already know what the limit's going to be, and you get to take out that little 0 is less than in the little antecedent clause of your conditional. Let's talk about some functions here and how these theorems can be useful in helping us characterize continuity. Remember that we said there was a sequential definition of a limit. There's also a sequential definition of continuity, which ends up being very important to us in future proofs. So a function f is continuous at a point C if and only if, whenever you have sequences that converge to C, you have f of x of n converges to f of c. You might notice, by the way, that this actually follows nearly directly from the sequential definition of a limit that we gave back in our previous discussion. Except notice that the last time we had to say, for example, x of n was not equal to c for all n. Now that's okay, because we can ask for our function to be defined at c. That's totally fine. And what's more, L has been replaced now with f of c. So this is a solid definition now, continuity, that comes very nearly directly from the definition of a functional limit. Also from the definition of a functional limit come the functions f and g whenever these two things are continuous. So are f plus g, f minus g, and fg at a particular point. If additionally, you know that your limiting point is not equal to 0, and indeed, you would need g of c to not equal 0 in order for this function to exist at that point, then f divided by g would also get to be continuous at c as well. So a lot of these come straight from the definition of a limit that we saw previously. Let's see some examples here of continuous functions. We've already seen a lot of examples for limits. Let's go ahead and see some for continuity. The ones that we get to use for free, essentially, for continuity is power functions. Now, why do we get to use power functions for free? Well, because we already know two things. One, f of x equals x is continuous. And we also know that the product of functions is continuous. And because we know these two things together, that is, x is continuous and x times x is continuous, as is x times x times x is continuous, because you have just two x's multiplied together. We already said that was continuous. Times another x is still continuous. You can inductively show that f of x equals x to the n is always a continuous function. Polynomials the same way. This time we can multiply times constants. Multiplying times constants, of course, that's two continuous functions. So that is also continuous. And you can add continuous functions together. So that is also continuous. All polynomials, hence, are continuous functions. Rational functions, the same way, as long as p and q are polynomials, and we're looking at places where q is actually defined, right? Or maybe better to say, actually, because q is always defined as a polynomial, I should say that q is not equal to 0. I take those points out of its domain, and then all on the entire domain of the rational function, the rest of the function is continuous. For example, that means that, and this is a little bit of a mind breaker for a lot of students who are just now getting into this, 1 over x is a continuous function. Now, it is a now we would not say that it's continuous at 0, but our response would be, we don't care about 0. 0 is not in the domain of 1 over x. Whenever we say a function is continuous, remember, we say it's continuous on its domain. We said that with square root of x, right? That is a continuous function. And we're saying the same thing here. 1 over x is a continuous function. Even though you have to pick up your pencil in order to continue drawing it, that was our intuitive and a little bit hand-wavy type of definition. This is a much more solid one, and it tells us that 1 over x is continuous. What if you had two continuous functions on either side, and you looked at the point in the middle? Would your function in the middle be continuous? Let's take a look at what this means. Let's say you have a function f and a point c that's somewhere splitting your interval into two pieces. Let's let f1 be denote the restriction of f to all from a to c, but including c, and f2 being all the way from c and going to b, again, including c. It turns out that if you have the two functions f1 and f2 being continuous on their own, then the function f is itself continuous, and vice versa. That is an if and only if statement. In fact, a lot of this comes from the fact that, remember, whenever we have these little endpoints here, you're asking for left and right endpoints, right, to be left and right limits only to exist for these things. So, for example, in order for f1 to be continuous, right, we would have to say that the limit as x approaches c, but from the left, for f1 of x is equal to f of c. And over here, we would have to ask for the limit as x approaches c from the right of f2 of x to be equal to f2 of c. In fact, I should be saying f1 over here as well, since these are, in this case, the same function. So whenever we say that f1 is continuous on the interval going from a to c, including c, then this is what we mean. Well, guess what? We have now a function f, which is formed by splitting these two functions apart. Well, if you split the two functions apart, there's one thing that they share, which is the point in the middle. That means that these two things are going to be equal. In that case, the left and right-handed sides are going to have the same limit. So our function is continuous at the point C. So that's exactly what this proof is going through and explaining. And a neat little application of that is here on the function absolute value of x. So far we've been seeing that whenever you have a function and you split it up into two parts, maybe this part here is f1, and this part over here is f2. Then continuity on either part, on either side, on the left or on the right, is going to give us continuity on the entire thing. And that's because of how we've defined continuity at endpoints, whenever endpoints are included inside of intervals. Now, the absolute value function works very similarly. You have a function on the left of a point, that point being x equals 0, and you have a function on the right. That function that is going to the right there. So you have two functions kind of being split up and saying, okay, well, what are these two functions? Well, to the left, we know that this is f of x equals negative x. We've seen this one before. And then to the right, we have that this is f of x equals just positive x. Well, both of these are polynomials and hence are continuous functions, and they meet here in the middle, and they have well-defined one-sided limits. Because of this, we have that this function is continuous. So this is a way that we will oftentimes be trying to employ this theorem, which is in looking at piecewise functions, much like the absolute value function itself. Now, compositions come back here because we mentioned that knowing something about the continuity of either of the constituent functions of a composition is really nice to help us figure things out. Let's see if we can figure out what that means. Let's be a little bit more specific. The theorem here is going to help us out. If f is continuous at a point C in its domain, and g is continuous at this point f of c, which is in its domain, because f of c, remember, it's been sent off, and now it becomes the domain of the function g. So this is g of f of x. That's an input function now for g. Then g of f is going to be continuous at our beginning point. All we need to kind of do here is just follow our nose a bit when it comes to looking at the sequential definition of continuity. So what we do is we look at an arbitrary sequence x of n, and we say, okay, well, if x of n is converging to c, then we know f is continuous at c. So what do we know? F of x of n converges to f of c. Now, f of x of n converging to f of c, now that is a sequence in the domain of g. That's going to tell us some stuff. Because now, remember, since g is continuous in f of c, we have f of x of n converging to f of c. So here's kind of our trip that we're taking. We start with x of n converging to c. Well, then we know from the fact that f is continuous that f of x of n converges to f of c. So we have this so far. Then we have another sequence now in the domain of g that converges to f of c. Well, guess what? G is continuous at f of c. So that means that by definition of g being continuous at that point, we have that g of x of n converges to g of f of c. And that's because we have that g is continuous. And then finally, putting all of that together, we know g of f is just the composition of these two functions. So that gets us what we're looking for. All right, pretty good, pretty good. So of course, once everything is nice and legally defined, this gives us a very good composition for the continuity of this composition here. Okay, so let's go ahead and see a few more examples here for continuous functions as we move along, employing especially this notion of composing two different types of functions, like the absolute value function, as well as any other function that you work with. Namely, if you have a function f, and you take a function which is the absolute value of that function, then that also ends up being continuous. Note that this can look like a rather strange function sometimes, right? You can have a function that looks a little bit like this, and then the absolute value of this function looks like something like woo, 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 yeah. So it's a little bit like kind of a strange, different type of function. This is f, and this is the absolute value of f. And you can ask, okay, are there any issues? Are there any problems that end up going on here? But the idea is that as you compose through these functions where absolute value takes over, it's continuous. Where the absolute value switches the polarity between types of your function is still continuous at that point. So everything is still well and good. Now, another neat way to kind of put this together is to say that whenever you have two functions that are continuous at a point, it turns out that these functions defined here, the max of two functions, f and g, and the min of two functions, f and g, also end up being continuous. Let's be specific about what we mean by these two functions. So here we've got these examples. This is for f and absolute value of f. Let's say that I have two functions over here, though. Let's see. Let's say that I have f and g. So let's call g something else. Maybe we'll make it something like this. Now, for a while here, it looks like g is going to be the maximum function. So if I'm taking the max of f and g, then for a while at least, it looks a lot like that the function g is taking over. But you can see that past this point, the function starts to dip a little bit while our function f is beginning to increase. So at some point, the functions are going to switch places. Something like this. So here you have that the two functions are going to switch places going from wherever g was the max versus to wherever f was the max. So it's kind of like you have two different functions that are stitched together at points wherever the maximum switches. If f is no longer the max, g becomes the max instead. Well, if f and g are continuous, And it turns out that that transition is seamless. Because what happens? Where do they meet? They meet and switch off whenever the two things are going to be the same, whenever f and g end up being the same thing. Intuitively, at least, that seems to make sense, but we want to be a little bit more specific. How can we be sure that max of fg is always continuous and min of fg the same way? The way that we do it is we define the function in this way. It turns out that the max of f and g can be written in this way. Well, here is two functions. First, notice that each term is itself continuous, so adding them together is going to be continuous. Here we have that absolute value composition thing that's very useful to us here. And notice that this right here is the average of the two functions. So this is the average of the two functions, and that this here is half the distance between the two functions. So in some sense, what you've done is if you have f up here and you have g down here, then your first function is just lining the middle here. But then you add half the distance. Notice you're adding it, so you're going to be going upward. And when you're going up to where f was. Your average is already half the distance between your two, either of your two functions. So you're just traveling up the remainder of the distance to get to f. Notice that if f and g ever switch places, though, that travel upwards is important, right? So for example, let me try and give it another picture here. I'm going to see if I can find another slide. So here is a picture for that. Oh, in fact, I had one upward. My apologies. Let me do it here. So for example, let's say that I had a function f that looks like this, and a function g that looks like this. Then the average of those two functions is just going to be what? It's just going to be this value, right? That's the value that's the average of these two things, if these two are lines. So if this is 1/2 of f plus g, then the rest of it comes from half the distance between the two functions themselves. So notice, for example, connecting these 2 points, half the distance, I can either go up or down that distance. Going up that distance gives me to f. Going down that distance gives me to g. Now that's different if I look over here, because now going up that distance gets me to g, but that's exactly what I want. It's the maximum of those two functions there, whereas going down gets me down to f. So there's a nice little picture there to get us to talking about how the max is defined. Notice that the min, the only difference is that you have a minus here instead of a plus because you're traveling down the rest of the distance from the average. Finally, we conclude that the max and min are continuous functions because they can be written as sums, compositions, multiplications of all continuous functions themselves. Neat little trick. Trigonometric functions. Let's return to these for just a second. We've got our sine, cosine, and tangent formulas as before. Again, here our circle is our unit circle. We've got our same little picture idea from before of sine theta, theta, and tangent theta that we were seeing back in our limit section. Now let's see if we can use those principles and help us remember examples of continuous functions now in terms of trigonometric. Sine and cosine seem to be the first place to start. Sine is itself a continuous function, and we can do some things to kind of help us out with that. The idea, of course, is that when we're trying to set these things up, we're starting by saying, okay, we want x minus c to be less than delta to give us that f of x minus f of c to be less than epsilon. Now, in this case, our function is sine, so I'm just replacing sine there instead of f. And so we are going to have to try and see how this sort of system works. Now, this guy right here, I do have a little bit of ability to work with. It's not that nice of an ability, but it is possible. Remember that when you have two values, and we've done this a little bit before, whenever you have something that is like, say, for example, sine times cosine of something else, right? Then you can write that as a sum and difference formula on the inside there. Right. So what we're going to do is attempt to do that, essentially. That's what you can see here in this proof. First things first, we know that sine of theta is going to be less than or equal to 1, and cosine of theta is less than or equal to 1. We did a little bit of that before. And we're going to use this trigonometric formula, which comes from the sum and difference formulas for these two things. Okay, so for example, you can notice here that 2 sine cosine, right? We have that if you add these two things together, you get x. If you subtract these two things, you get c. Putting those things together, you get this formula from all of that. That is something that is worth checking if you'd like to do that. So what does that mean? If I can rewrite this in this form, now I have something that maybe I have a little bit more control over. Because remember, what I get to work with is the fact that x minus c is less than delta. So if this becomes small, then I have this is 2 times sine of x minus c over 2 times cosine of x plus c over 2. Now, remember that cosine of x plus c over 2, that's less than or equal to 1. So I can ignore this. However, sine of x minus c over 2, remember that's less than or equal to x minus c over 2. We're using this part right here, or rather the part with the absolute values in it. So here we're using this formula to help us get to this. Well, if I multiply all that out, I get the absolute value of x minus c. So, in fact, whenever I'm doing my little delta and epsilons, it's okay for me to just like delta equal to epsilon, because that gives me everything that I need. Sine of x is going to approach sine of c as x approaches c. We notice, by the way, that only thing we have to do for cosine to show that this one is continuous is notice that if you shift cosine over enough, you get a sine function. So this is a composition of two continuous functions, one that is a shift function and one that we've just proven to be continuous. All right. For the sake of notes later, I'm just going to cross this out because this is less than or equal to 1. There we go. Some nice little bookkeeping for later. Continuing on, we have that whenever tangent is defined, at least on its domain, and again, that's the only thing we care about, is that our function is a quotient of two continuous functions. So tangent is going to be continuous on its domain, of course. Then we have the function f of x equals sine of x. Now notice this one is not continuous at x equals 0. So we're going to have to define the function to be something else at 0. And what we're going to do is we're going to define the function here, f, to be at 0, the limit of sine of x over x as x approaches 0, that limit being 1. Well, if you define that, then everything else follows suit. For anything that's not equal to 0, you have two functions at which the bottom limit is never 0. So that is always continuous there. And then at 1, we have all three things that we need. We have the function is defined, we have the limits defined, and the fact that the two things are equal. So that works very well for us to show that this is continuous at 0. Let's move on to what continuous functions get us. And this is going to get us to one of the big theorems that we talk about in Calculus 1, and that is the intermediate value theorem. But the intermediate value theorem, recall, is the one that says if you have 2 points on an interval and your function is continuous on that interval, then whenever you look at maybe the 2 points, the y values of those 2 points are somewhere where this is here and this is here, then any points inside of those 2 points in the y direction, any y value in between these two y values, that does have some x value that maps to that y value. So it has to hit every single y value on its way from one end to the other. So we're going to see that as we're going to build up to that as we see some of these theorems here. If I is a closed and bounded interval of the real line, closed and bounded, those two words end up being important in other contexts as well. Closed and bounded interval, then any continuous function f is bounded on the interval I. That is, f of I is going to be a bounded subset. Right? The idea here is going to be based off of something that you might be familiar with called uniformly continuous. You might recall this from some other sort of course. What that means is this: f of I is a bounded subset, but it's also going to attain its maximum and its minimum. The idea is that you should have sequences that are approaching the maximum and minimum thanks to the fact that you're on a bounded set. This is thanks to something called Bolzano-Weierstrass. So this is going to give us extreme values for this interval. And then finally, if a function f is continuous, then any number y naught that lies in between its y values at its endpoints is going to have a value that maps to it. This one is what we know as the intermediate value theorem. And here and throughout the rest of the course, it'll be common for us to talk about this in terms of IVT. So this will be how we can write this. Now, the extreme value theorem is one of those things that we just discussed. So here it is again. There is, let's see, any continuous function attains its extreme value. That is, that there exist function values or actual values inside of your interval such that if you map that one x value, look at its y value, then everything else in the function is going to be greater than or equal to that function value from the minimum. Same thing for the maximum, except you're flipping the inequality. The theorem does not have to hold if the interval is not closed, however, which is where that part of being closed ends up being important. And again, the Bolzano-Weierstrass asks for that in its conditions. F of x equals x, for example, where x is the open interval from 0 to 1, does not have a maximum or a minimum, right? And the theorem can also not hold if the interval I is not bounded. For example, the function 1 over 1 plus x squared is function limits to 0 as x goes toward infinity, but there is never a point on this function where the function equals 0. So that is a kind of another condition, another way to think about this. So we used this very briefly in Calculus 1 to discuss finding max and min. We did first derivative test, remember this? Where we were talking about how we could bring together and find maximum and minimum, optimize certain problems, find ways to connect real world applications to calculus. This ends up being one of the big things that we can do, and that comes from this extreme value theorem. The extreme value theorem ends up being very important in this way. Then we have the intermediate value theorem, which is going to become important to us in a few different ways as well. And we'll see those as we continue to progress through this course. The theorem, the idea, of course, is that if a function takes two different values, then it also takes all values between them. Now, I was very happy to see that in my course collection and compilation here, that there were some notes here that I could scrounge around and find from very interesting sources. And again, I cannot take credit for this. This came from another instructor, and I really appreciate it. But we'll get to some pretty nice things once we talk about the intermediate value theorem a little bit. But first, let's talk about some corollaries. If a function is defined on an interval I that takes two different values, it also takes all values between them. This is one in which we can definitely use the intermediate value theorem here. So we'll talk about this picture again, because this one's a little bit easier for me to draw since I just have a function that is on an interval here. Says that if I have points, and this function can be however it wants to be, go all the way to here, then there is always going to be a point, an x value, that maps to any other y value, right? This is some y, where y is somewhere in between f of a and f of b. Maybe better to say that it could be the opposite direction as well. So something like this. Right. So whenever these two things are not equal, we want to show that f of c is equal to s here. So what we're going to do is we're going to take and find a continuous function that ends up working nicely here. Before, we had continuous functions going from the real numbers, and the only thing that we really need to do is to consider a way to take a function that is an interval like this and make it go be a function on the real numbers. So this is just going to be a little trick of extending the function. In order to make it not have an interval, but instead have the real numbers as its domain, I just have to tell you what the values of the function are to the left and to the right of this interval. And the way that I'm going to do that is I'm just going to say it's constant. It's just going to be constant, going either direction, to the left or to the right. If I do this, I still have a continuous function. Piecewise, it's still continuous from the left and to the right. We know that from a previous theorem. And so, hence, because these function values are two values somewhere on the function, it's going to take that point in between there somewhere, right? And clearly, it cannot take that point over here or over here because we didn't ask for y to be equal to f of a or f of b. We wanted it to be something in between there. So that point that it takes is somewhere inside of our interval. Also, we have that any continuous function maps intervals to intervals as another corollary of this, right? Because why? We have, whether we're looking at f of a is less than y is less than f of b, or f of b is less than f of a is or less, f of b is less than y is less than f of a, whatever kind of collection that we're looking at, we know that there is always an x value that maps to this point. Well, that means that you're going to have the collection f of a and f of b at least as a subset of your range inside of here, right? And the same thing is true, by the way, if you looked, instead of looking at the endpoints, if you looked at the max and the min. If we had replaced this x min and x max here instead, then in fact, this is also going to be a subset of f of I. Well, this is also, by the way, going to be equal to f of I because f of I can't go any lower than the minimum. It can't go any higher than the maximum. So indeed, f of I is going to be an interval, and it's going to be formed in this sort of way. Now that works regardless of the case that we're working with. This time, we're replacing A and B with x min and x max. And that's thanks to the extreme value theorem that we talked about before. So here's a little question for us. And again, this is not my idea, but I enjoyed reading this, of how we can go through and look at the intermediate value theorem through some applications, if you will. Sam and Frodo's journey to destroy the One Ring follows the elevation path in thousands of feet, given by the function f of t equals negative t cubed plus 2t squared plus 3t. Their 2-day journey from the gates of Moria at sea level to the other side of the Misty Mountains, 6,000 feet higher. Did they pass over the bridge of Khazad-dûm as they made their way through the mines of Moria, which was an elevation of 4,000 feet? Now, what we're trying to show here is that there is going to be some point in this function that actually gets us to 4,000 feet. Right now, what we know is that we have a journey that starts us at 0 feet and gets us to 6,000 feet. So what would we expect to be the answer? We would expect, yes, absolutely, that it would get us to that elevation of 4,000 feet. Of course, for some reason, we're just considering that you have to pass through the mines of Moria. That's the only thing at elevation of 4,000 feet. You couldn't have just gone around it. No, definitely not. But that's all that we have to do. We're saying that on this function, you see here at the endpoint here at 0, you start and get to point 0. That's 0 thousands of feet. And at f of 2, you indeed do get 6. So that's going to be at 6,000 feet. So since 4 is in between 0 and 6, there's got to be some point at which you did reach f of c equals 4. So Sam and Frodo did pass over the bridge of Khazad-dûm on their way through the mines of Moria. Just a fun little example here with the initial value theorem. And again, very excited about all of this because you kind of get to see a little bit of like, here are the neat little ways that you could be teaching and finding ways to make this fun. I really enjoyed finding these little slides here. Not my creation, and indeed, this meme is also not my creation, but one does not simply travel from A to B without passing through C. See what I mean? It's a fun little way of kind of making this stuff all connect together. So, and the thing is too, is that Lord of the Ring memes, always timeless. They always work so well, regardless of your context. So let's go through and see another example here with regards to continuity. So let's solve this question. Let's solve this question here. Let's prove that there exists a unique real root of the polynomial x cubed plus x squared minus 1 equals 0 between the points x equals 2/3 and x equals 1. Let's prove that exists a unique real root of the polynomial given here. So basically a point where it equals 0, so I don't need to write that there, between the points x equals 2/3 and x equals 1. So a real root, again, is going to be a place where this polynomial equals 0. So let's see if we can go through and find that. Well, if we are now collecting what we know from the intermediate value theorem, we can start by trying to say, okay, well, what is p of 2/3? What is p of 1? Maybe we can start by just trying to plug in endpoints and see what we end up getting there. Well, if I do that, I have 2/3 cubed plus 2/3 squared minus 1 should be 8/27 plus 4/9 minus 1. Getting all of that over 27 should give me something like negative 7/27. So that's a negative point. I would hope that p of 1 would then be a positive point, because if it were, then maybe I could use the intermediate value theorem here. So what I'm going to do is just plug in x equals 1 here, get 1 cubed plus 1 squared minus 1, which is indeed 1. So since negative 7/27 is less than 0, is less than 1, there exists a point C, which exists inside of 2/3 and 1, such that f of, or rather, p of c is equal to 0. So that gets us where we need to be. So that at least gives us existence. Now, this is only part of our proof. Notice that it said there exists a unique real root. So we're actually not quite done here. And so what I'm going to do is I'm going to break off this part of the proof as the existence part of the proof. And let's do uniqueness down here. Now, how are we going to show that this is the only point inside of the interval going from 2/3 to 1 that equals 0 here? How do we know that there's not like a little, a little wave that takes place that has it crossing 0 multiple times? So let's assume there are two real roots, and I'll call them C1 and C2 within the interval going from 2/3 to 1. And the question is, what can we say about that? Without loss of generality, I can say that since they're two real roots, and I'll go ahead and make a kind of a little bit of a nuance here. I'll say that they're distinct in this case, just to say that they're different. And if I know that they're different, then one is going to be greater than the other. So I'm just going to go ahead and say C1 is less than C2. Well, something that I know about that is that since C1 and C2 are both greater than 0, then C1 cubed is greater than C2 cubed, as is the case when I replace cubed with squared. C1 squared is also less than C2 squared. So what do I know if I add them together? C1 cubed plus C1 squared is less than C2 cubed plus C2 squared. Maybe you see where I'm going with this. Because if I subtract this by 1 on both sides, then what I end up getting is something that maybe looks a little bit strange. Didn't I just say that C1 is a root of the polynomial P? But this is actually P of 1. So this is supposed to be equal to 0. But this, on the right-hand side, this is, P of C1. This is P of C2, which is also equal to 0. So how can it be the case that 0 is less than 0? And the short answer is that it cannot. This is a contradiction. So there is, at most, one real root. And that's because we have here that 0 is less than 0, and that gives us our contradiction. Okay. So putting these two statements together, the existence part says there's at least one. This one says that there's at most one. That tells us that there exists a unique one. So it's the only one available. Let's finish off by talking about ways in which a function can be discontinuous. What are the ways that a function breaks the definition of continuity? You've seen some of these things before, perhaps, but we'll go through and make sure that we're understanding the differences that is meant in the definition here. Well, one, remember there were three conditions. One is that the function does not have to be defined at a point. It doesn't have to be defined there. And sometimes we call that function a whole, depending on what it looks like around it. We're going to say that a function f has a removable discontinuity. This is going to be very similar to that. If the limit exists, it looks nice around the point, but the function value is different at the value of c. Okay. Now here, for example, E is going to be our domain, and C we're assuming to be inside of the domain. So we're not trying to cut any corners and say, oh, there's just a hole here at the point. Here we're going to say that the function is defined. We're just going to say that it exists somewhere else. So a removable discontinuity, for example, would look something like this. You'd have a function that is like this. And maybe it has a little bit of a hole there, but remember, we're saying that the function is defined on its domain here. So the function, it just exists somewhere else. It's just popped out for a little bit. Here you can see the limit exists elsewhere. So that is known as a removable discontinuity. A jump discontinuity looks very much like what we had in a previous example, very much like this one. Right here, you have that the limit around it does not exist. You have both one-sided limits exist, but they are not equal. So here, for example, this would be an example of a jump discontinuity. Notice that I added the function value to still exist at that particular x value there. So this is an example of a jump discontinuity. The two limiting values exist, but they are not equal to each other. This point, by the way, could have been here, could have been here, could have been anywhere else, and we would still be looking at a jump discontinuity. Now, any other discontinuity of f is called essential, and examples of essential ones are much like sine of 1 over x. Maybe you have to define it a little bit more carefully, but you could do something like this: f of x equals sine of x, sine of 1 over x whenever x is not equal to 0, and say 0 when x is equal to 0. Here, the functions do not have one-sided limits going from the left or the right, so this is an essential discontinuity here. An example of another essential discontinuity is a point at which the function is not locally bounded. That is, f is not bounded around the particular point that you're trying to have your function at. Notice that this one here, this is locally bounded in our definition, but an example of something that is not locally bounded is if we had taken that same example, the sine of 1 over x and 0, and divided by x, then this would not have been locally bounded. So that would have been another example. So that gives us a few ideas behind what all kinds of ways that our function can be discontinuous. Removable, in some sense, we've talked about, the way I think of removable is that there's just a hole there, right? Then the way that you remove the discontinuity is you just take the point and you put it back in, right? So that is, you've removed the discontinuity. Jump discontinuities are a little bit trickier to work with because you'd want to say just take the functions and smush them together, but there's a little bit more work there. There's a jump that it takes in order to make something like that happen. You have to jump from one line to the other. An essential discontinuity means that a good bit is going on. There's something else that's happening in this sort of discussion. Now, we've already discussed half continuity a little bit, because when we say that a function is continuous on a closed interval, if and only if it's continuous on the interior of that interval, together with at the endpoints, at the left endpoint, the right-handed limit exists and equals the function value. And on the right endpoint, the left-handed limit exists and equals the function value. So that is a notion of right continuous and left continuous, respectively. We say that it is right continuous at A, which means that for any points that are to the right of our value of C, then we have that it satisfies the continuity condition. Then, at the right endpoint of our interval, at the endpoint B, we say anything to the left of that satisfies this continuity consequent. So right and left continuous are very useful in showing when a function on a closed interval is going to be continuous. It is right continuous at A, and it is left continuous at B. Okay, so those are two ways of using right and left there. Now, upper semi-continuous and lower semi-continuous are interesting because they're not asking us about anything with regards to x. You can see here that our antecedent parts of our conditional statements are staying the same. What is different, though, is that we're saying that whenever your y values are approaching from above, or rather upper semi-continuous means when they're approaching from below, that at least it doesn't go too far up from the function value. It can go below, but it cannot go above. F of x minus f of c is bounded above by epsilon. Here, lower semi-continuous is when f of x minus c is bounded below by negative epsilon. The function cannot dip too far down. A notion of this that is a little bit interesting here is what kinds of functions would be upper semi-continuous or lower semi-continuous. Let's take a look at an example here. Let's do it slightly differently. Let's do it like this. There we go. Now it has a little bit of an incline. And the question is, first, is this function left continuous or right continuous, or neither? Using our definitions of left continuous and right continuous, we can check to see if this function satisfies everything that we want for one of those two conditions right here. This one ends up satisfying the left continuous condition, because as you can see, for any x value, there's going to be some points over here on the left that still seem to approach the value. And that same thing is true right here. So this is a left continuous function. However, this is not right continuous, because at this point, any of the function values to the right They certainly do have that one-sided limit, but they do not approach the function value. So this function is left continuous, but not right continuous. Now, is this upper semi-continuous, lower semi-continuous, or neither? Is the next thing. Let's use the definitions to try and help us out here. Remember that we say a function f is upper semi-continuous if whenever you're looking at the difference between the function value itself and the function that you're looking at, that there's an upper bound on that difference, f of x minus f of c. Now, f of c is down here. This is where f of c is. So let's analyze here at this point of c. The question is that around this point, do I have that there's an upper bound on the function values as I look around at this point? That is there an upper bound on the value of f of x minus f of c? And can I make that upper bound be as arbitrarily small or close to zero as I would like it to be? And the answer is no. If I make my epsilon to be of this length, notice that the only heights that the function can go toward is that it has to be eventually inside of this neighborhood of c. It needs to eventually be inside of there, and it is not. In fact, this whole part is outside of this interval. So no delta that I choose is going to allow me to get inside of this epsilon. So this is not upper semi-continuous. Now, is it lower semi-continuous? Let's ask that question. So now we're going to try and rewrite this a little bit. There we go. Is it going to be lower semi-continuous? We are now asking, is it the case that f of x minus f of c is bounded below by some epsilon? So again, we take a look here at these parts here for this particular neighborhood that I'm just arbitrarily choosing to kind of get us an idea, and asking the question, is it true that the absolute value, or that f of x minus f of c is bounded below by something? Well, notice that the values of f of x up here are fine, because f of x minus f of c is positive. That's automatically greater than a negative number, like a negative epsilon. So I don't have to worry about the numbers up here. The thing I'm most concerned about is the number up here. The number down here, rather. I want that number down there to be pretty small. Well, and I can make that as small as I would like to. For all epsilon, there's going to exist a delta. I can just make this delta narrower so that I'm eventually within the epsilon window coming in from underneath the point. So you can think of this as like, it's okay if the function is all the way up here in this part of the function. So that is okay. So this is lower semi-continuous, because the function within that little epsilon window, that little delta window, does live in that little half plane given by a value that is just a little bit less than f of c. Okay. So this is not upper semi-continuous, but it is lower semi-continuous. It is left continuous, but not right continuous. And you can kind of play around with this exact example and try to find other different types of functions that are upper semi-continuous, but not lower semi-continuous, or right continuous, but not left continuous, and any combination of those as well. So some examples here, step functions. This one going from 1 to 0. This one has a jump discontinuity at 0. It is continuous everywhere except 0. And then it is left continuous from the left and lower semi-continuous. So using this kind of makes sense that it kind of is since it equals 0 there, it makes sense that it'd be left continuous. It's continuous from the left. And it's also continuous coming from the lower end of this function. So that is the combination there. But we know it is not right continuous. We know it is not upper semi-continuous. Then there is the integer part function. You can see Bilbo Baggins coming up on the bottom of the screen. You know it's coming back. F of x equals the floor function is another way that this is called. For example, we know that what this does is it takes numbers like 1.5 and it just gives you the integer part. It just gives you 1. So this, for every integer, we have f of x equals n. And so the limit as x approaches n from the left of f of x is going to be 1. Checking something here. This should really be something else. 1 second. Okay, I've changed it. So the limit as x approaches n from the left should be n minus 1, and the limit as approaches n from the right is n. You can see that here with this little picture of Bilbo Baggins's age as a function of time. Pretty fun there. So the age, regardless of how much time passes, you can see that age remains the same. If you're 2.5 years old, you still say that you're 2 years old, if you can talk. So you have 2 years as this. You can notice that as I approach 3 from the left, that really my age or my limit of ages goes toward 2. But it's only if I approach from the left. If I approach from the right, then I'm already past my 3rd birthday. So I would say that I am 3rd age of any time that I'm coming in from the right. So you can see here, there's a jump discontinuity going on at each integer here. So this is continuous everywhere except the integers. And you can notice that this one is upper semi-continuous on R. As I fall down the stairs, if you will, the values are continuing to work well, at least from coming up, from up in our continuity definitions. And these are good things to kind of go through and check. A couple of other examples to start getting us ready to finish and close out here. We have the function f of x equals 1 over x, which is not defined at x equals 0. But if we just pop in that f of 0 is equal to 0, what do you think is going to happen? Well, the function does not have has one-sided limits that do not agree. The function as x goes to 0 from the right for 1 over x is infinity. And then from the left, it's negative infinity. So just popping in 0 there isn't going to fix anything. The function is still discontinuous at this point. We can also show that that's true because it is not locally bounded at 0. That's another neat way to show that. Now, on the other hand, if we had f of 0 equals 0 and f of x is sine of 1 over x, now we can start asking questions about this. Notice that this one's an essential discontinuity. We've talked about this one before. The function is continuous everywhere that we're not looking at 0. If we had redefined f at 0 so that f of 0 was greater than or equal to 1, this is a good thing to kind of go through and check. You can see that this makes the function upper semi-continuous on R. Redefining f at 0 to be so that f of 0 is less than or equal to -1, you can see that that makes it lower semi-continuous. The idea being that as you're approaching from either side, at least a point beneath the function in its entire range still gives you the notion of it being lower semi-continuous from what we were seeing from before. And putting it above the entire range of the function, so that's greater than or equal to 1, around the range of its entire oscillations, that gives you something that still satisfies the upper semi-continuous definition because we have very nice lower bounds for f of x minus f of c. So a neat little way to see that. Notably, when you have f of 0 being somewhere in between -1 and 1, it's neither. It is not lower semi-continuous or upper semi-continuous in that example. And then the Dirichlet function. Here we know the limit does not exist anywhere. We've talked about that one before. So the function has no points of continuity. It is upper semi-continuous at rational points, and it is lower semi-continuous at irrational points. You can think about kind of falling from upward versus falling from downward and seeing those different types of examples. Then there's the Riemann function. This one is kind of a little bit cool. The Riemann function ends up being continuous only at irrational points. Now, why does that make sense? Do you remember that we said from before that the limit as x approaches c of f of x was always 0? And that was true regardless of if you're at a rational point or irrational point? Well, if the limit equals the function value at that point, then we know that the function is continuous there. Well, remember, irrational points, that's exactly how the function is defined. It's defined to be 0. That is exactly the limit of the function at that point. So this is a function, we found the existence of one, that is continuous only at irrational points and discontinuous at every rational point. Moreover, all discontinuities are removable because one-sided limits exist everywhere. In fact, the whole limit exists everywhere. You can also show that the function f is upper semi-continuous on R. Right, so that's going to kind of do it for us today. We've discussed a lot about how we can talk about continuity, ways to prove things with continuity, ways to use the intermediate value theorem and prove things using that. And finally, we've seen some examples of all the different ways a function can be discontinuous at a point. That'll do it for me today. Thank you so much. Have a wonderful day.